In this video, we're going to walk through one of the problems that we talked about in class about a change of variables problem for double integrals. This is problem 14.8.14, so problem 14 from section 14.8. And I will go through the written solutions, and then in the video tutorials, I'm going to include this video. And also in our shared Mathematica files, I've put the Mathematica code that I use to solve this problem and set it up completely. So in this video, we'll just go through the written solutions. I've handwritten these before, and I'll just try to talk you through them. These solutions are in the notes also after the problem statement. Let me show you that. So after the problem statement, here is the solutions that I'm going to show you. So we're being asked to find the double integral of this function over the region R. The region R, they gave you four different lines, and they make this parallelogram, this slantwise parallelogram. And they were given us the transformation. This transformation T of uv was given. And it was up to you to find the transformation which takes this rectangle in the xy plane and turns it into a new region in the UV plane. So if you go through that problem and use this transformation, inverse transformation, I'll do some details on this in a second, you will find that this region becomes a nice rectangular region in the UV plane. So the steps for doing this integral in new coordinates, so to change this variable over from xy space to uv space, otherwise known as doing a uv substitution, you need to take the function and just change the variables. So wherever you see the function f of xy, wherever you see x, you put in what they gave you for the transformation. X is equal to u minus 2v, and y is equal to 2u minus v. So you put those in for u and v, and you have a new function to integrate. This is what your new function, 8u minus 7v. But that's not all. You have to compensate for this change of variables by bringing in the derivative of the transformation. The derivative of the transformation is given by the Jacobian. It's given by two gradients stacked on top of each other of the two entries of your vector valued function, which is your transformation. When you compute the determinant of the Jacobian, you get 3. So here you put these two steps together, and we now need to do a du dv or a dv du integral of the function times this compensation term, and we need to integrate over this new region S in the UV plane. The region S in the UV plane is given by this rectangle, as I've kind of hinted at. The hard part of these problems is to actually figure out what the transformed region in the UV plane looks like, and that's step 3, and this is where the majority of your time will go in. So note that they gave you this transformation, and in this transformation, for example, if you pick a UV value, you can find the x and y value. So if you pick u is equal to 1 and v is equal to 2, you plug u equals 1, v equals 2 into your xy equations, and you get x is equal to -3 and y is equal to 0, just for these points, for example. But what we really want is to know how the point in the xy plane in this region moves over to a uv value. So we need the reverse of this transformation. We need the inverse of the transformation, which tells you if you give me an x and y, how do I get a u? If you give me an x and y, how do I find a v? And to do that, we need to find u and v in terms of x's and y's. And that's a straightforward algebra solve. So for example, take the two equations you were given, multiply 1 by -2 so that you can get 2v, and then you can add those two equations to get x minus 2y is equal to -3u, and then you just solve for u is equal to this expression. Similarly, you can solve for v. And these two expressions are where I wrote down here the inverse transformation. That's what I put in the 2 entries here for your inverse transformation. Okay, so I've shown you how to find the inverse transformation using an algebra solve. Now what you need to do is the part where you transform each edge of the xy region and transform it into the UV plane. So really straightforward process. L1, we're going to call this line. I'll do one example for L1. L1 is just the line from P to Q, so here's the equation of that line. And simply, this is what you get. -2 plus 2t is the x value. X is a function of t, and y is a function of t is -1 plus 4t. So note that when t is equal to 0, you're at the point -2, -1. And when t is equal to 1, you are at the point 0, 3. Okay? So now you transform this line by putting into your inverse transform, wherever you see the x in the inverse transform, you put -2 plus 2t. Wherever you see the y in the inverse transform, you put -1 plus 4t. Okay. So that's what we're doing here. We're using the inverse transform, putting in x and y, and simplifying, and all that simplifies to the vector 2t comma 1, which is another line, but it is a line now in the UV plane. That line, when t is equal to 0, put in t equals 0 into here, and you get 0, 1. So here you are at the point 0, 1. That says that this point P in the xy plane, that's where you were at t equals 1, 0. But when you transform that point, this point P becomes that point right there. And at t is equal to 1 in this equation, you're at the point 2, 1, which is 1, 2, 1. But this is in the UV plane. So this point Q, which is where you were at t equals 1 in the xy plane, becomes this point right here, 2, 1 in the UV plane. So this edge of the parallelogram is going to map or turn into or transform into the top part of this rectangle. So that was the rectangle that you were given. If you take the other 3 sides, you will turn into this rectangular region. Okay, and that is up for you to show the other parts. You should transform the other 3 sides, and you will get a new region of integration in the UV plane as this nice rectangle. Okay, so we're now pretty much almost finished with the transforming. We had done in the first 2 steps, we had these 2 pieces, the function and then the compensation term with the determinant of the Jacobian. We just hadn't picked an order of integration, so let's pick du dv. And the order of integration doesn't matter because we're integrating over a region in the rectangle. So du dv or dv du would be equally as easy. And u goes from 0 to 2, and v goes from 0 to 1. And that is a really easy integral to compute, and it computes to 27. If you had tried to compute this problem in rectangular coordinates, you would have had to compute 2 integrals, because the region would have split as a top and bottom function. The top and bottom function here changed, okay, over that region. So you would have to compute this as 2 integrals. None of these are really hard, but they're not quite as easy as the transformed integral. And you would find that you will also get 27 for this integral. So you're supposed to get the same answer, which you do. And that's transforming a double integral in xy coordinates over to a equivalent integral, equivalent double integral, but in new coordinates uv. Okay. I have here, I've split this problem out in Mathematica. I split the problem up into all the steps here. Notice that, I'll just walk through here, I'm making my function. I had found each of the edges, okay, those were given to you. I found the points at the corners just by by setting these equations equal to each other and figuring out where they intersected to find the four corners. This transformation was given to you, and I just copied here in this place. I made u and v functions of x and y. So this is what you had to find. You had to find the inverse transform. Okay? So I've made my two vector valued functions, t and t inverse, as vector valued functions. There are two entries to these vectors, and each entry is a function of two variables. So this is a vector valued function in two variables, which are, for our purposes, are change of variables formulas. And this little piece of code will just kind of organize the information for you well in the plot. So here's your problem setup. You're trying to just define the region. Okay, so you can minimize this now. You could then go to plotting the region, which is pretty straightforward. I'm just going to plot these functions, and I'm going to do a region plot, and there are two of them. So I'm just doing two region plots. Okay, I'll show you what the plot summary looks like. There are 4 points. I'm just plotting the 4 points as corners, and I'm putting all these plots together. Okay, and then I'm just defining each edge as a line. So these are simply just my line formulas for the edges. Okay, so that's enough to define the region R. There's the code for it. I'll let you look at this file on your own a little more carefully if you would like to modify it. We now are going to transform the region, and so L1 was our line. We had 4 lines for each edge, and I'm just going to use the transform to put each entry of the line into the transform formula. So this is the syntax for transforming each edge. Okay, I'm going to plot each of those edges as a parametric plot because they are just new lines. They just happen to be lines now in the UV plane. So I'm going to label the plane U and V. Okay, and I'm going to do a region plot command. And there's only one region because it was a nice rectangular region. And then I will show the plot for all those together. Okay. So here I've put all the plots, kind of split them up into little sections, and now you can bring the plots all together by showing everything. And here's a plot of your region. Okay. As I said, this big parallelogram region splits into two pieces, the light gray and the dark gray, because the bottom function here is 1/2 x and the top function is 2x plus 3. But when you get past x is equal to 0, the bottom function switches to 2x and the top function switches to 1/2 x plus 3. So that's why you need two regions, because the bottom and top function are switching. And here's your transformation, inverse transformation that I said. There's a little code above that makes it look, condenses it and puts it in a nice format. The Jacobian, here it is, and the determinant is computed for you. And here is a plot of the transformed region. It's just a rectangle in the UV plane. If you wanted to look at the 3D region plot for this, there is your plane. We are trying to find the volume above that parallelogram region, but below this plane, 2x plus 3y. And I think you can see here I've split the two regions into two pieces. There is one over the gray region, that's this region, and one over the dark gray region, which is this bigger one. So you can see that the problem splits into two pieces, and I just want to find the volume of each of them separately. Okay, so that's the problem set up and putting all the plots together. The next part is just to compute the integrals, and those are simple. Here is your function. Okay, the first step we needed to do was to put 2x plus 3y to put the x and y in terms of u and v, and that gives you 8u minus 7v, and that is what I have done right here. I've just put the function evaluated at x and y in terms of u. I had my compensation term, and then my integral du dv goes from 0 to 2 and 0 to 1. The computer easily handles that one to give 27. And if you tried to stay in Cartesian coordinates, this is what you would use. As I said, the bottom and top functions change, so there are two different regions you have to compute, and that integral also comes out to be 27. Both of these integrals, no matter which way you set it up, you should be able to compute these integrals by hand. These are nice and easy to compute by hand. So that is longish problem, but I think the more you practice them, the more easy they get. And this is section 14.8, number 14. And that ends this video.